this lecture, we're going to introduce before this one, we introduced the propagation of the electromagnetic waves and the interactions between the EM wave with the atmospheric constituents. So now for this lecture, we're going to introduce the meteorological radar system, the measurement by the meteorological radar system, and also the methods to improve the data quality. So for the weather radar systems, we really needed to, based on the measured or the recorded data, for example, the voltage or the complex voltages, we wanted to obtain the moment data for that. That is used for the analysis of the weather conditions. So it is in here. It is also very important to know the critical issues related to the measurement. So, for example, the sample errors in the moment estimates. And the second is the noise effects in the measurements, or the noise effects in polarimetric. Measurements. And the third one is the, for example, the cloud contaminations. And also as mitigation. So all these things can affect the our measured data based on the weather radar systems, and so it is very important to for the signal processing and the cloud detection and the filtering algorithms that used for the at the research side. So firstly, we want to do is we wanted to start from a typical weather radar system that was developed by in the United States. So this radar system is shown here. So this is the diagram of the radar system, and it is called it has a name as WSR-8HD system. Okay, and its full name is called the weather civilian weather radar. Surveillance radar. It was developed in the 1988, so it is 88. And it's also a Doppler radar. It's here. So it has it operates in HESR mode. So it means it has two receivers here. This one and this one, and only one transmitter here. So for such kind of the radar, it's used for the dual polarization measurements, and it can be used for, it can achieve the better measurement than the single polarized configurations because it can offer the insights in the such as the shape, the orientation, and the type of the hydrometeors. So it offers a very good applications, and also until now we still have some applications based on this one, and its operating frequency I think is in the S-band, is around 3 GHz, and it can offer some physical properties such as the first thing is the reflectivity, right? We already use the capital V to represent that, the reflectivity. And also the velocity, and also the for the reflectivity is the typical reflectivity and also the differential reflectivity here, and also the correlation coefficient. And the last thing is the phase, all right? And here is the differential phase. So all these things, it offers the insights on the weather conditions, and based on for the systems, it has just besides the transmitter receiver and has antenna, and also the digital signal processor, and also the communication server, and for the communications with the interface, the user interface here. So for this system, the maximum limitation for this system is if it wanted to finish a complete volumetric scanning, it's gonna need 5 minutes for volumetric scanning. So which is appropriate for the such as the our typical weather conditions, but for the severe weather conditions, this time is too long, right? So we really need a much faster scanning methods. For example, by using the phased array antennas, which can offer a much faster beam scanning or beam forming, and so. But here, this device is the most typical setups that we already used. And after that, what we wanted to introduce is we're gonna start firstly from the expressions, how to calculate the parameters, the reflectivity, the velocity, and the correlation length, differential phase, all these parameters. So now let's first start from a typical electromagnetic field or the electric field that we introduced previously, or in the electromagnetic fields. It can be expressed as the transmitted side, so we use the capital E to represent T, subscription T, to represent that. And we assume it allows the radial direction in the spherical coordinate system, and it can be expressed as this one, right? So because it is a spherical wave, so we have a term, all right, and spherical wave, it has minus j times k times r, like this one, right? So another thing is amplitude. So we use capital A to represent its amplitude theta and phi, right? And also, there is another term that corresponds to as direction of the electric field. We usually use this one to represent it. So here. So this term is related to as polarization. Of the electromagnetic waves or the electric field, and A theta phi is the magnitude of the field. So now we have the expressions for the electric field. We already wanted to see how the power performs, right? So we have the expressions for the power density or the power flux. So it equals, the first thing is there is an absolute value of amplitude and square, right? This term. The second term is it should be divided by intrinsic impedance. And also, another thing is it propagates along the radial direction, like this one. Right? So it's along the radial direction here. So this is how the power density flows or power flux flows. And we know this one, and if we take integration for the power density with all the solid angles, then we can get the transmitted power. So the transmitted power PT, it can be expressed as capital P. It can be expressed as S T theta phi, all right? And the times the area and over the closed solid angle, and we can express it as the solid angle can be as the area of the solid angle, so it can be expressed as 4 pi over the solid angle st theta phi times r square, right? The omega, and its direction is along the r direction also. So then it can be further expressed as a form like this term as 1 over 2 heat node A theta phi square d. Right, so this is the expressions for the transmitted power, like this one. So when we get this term, then we can also calculate the gain, right? So the gain of the channel, it can be expressed as J theta phi. The gain of the channel is the the ratio of the actual power density with respect to the power density related by a source that radiates uniformly to all the directions, like that one, and so it can be expressed as the transmitted power divided by all the directions, and it radiates uniformly, right? So here is the power density as we previously demonstrated here, square divided by 2 eternal. Yes. So this is the expression for the antenna gain. So now we can combine all these expressions. We can obtain the transmitted power, the electric field. Sorry, it can be expressed as finally as the by the transmitted power and times the is expression minus j k r and d the direction of it, right? So the first thing is the ET times the ET node over 2 pi, right? So this is electric field is the square root of that one times the antenna gain, like this one, this one, this one. So this is the electric field, the transmitted wave field. And for the receiver side, the received power is the received power density times the effective of the antenna area, right? So the effective antenna area, the receiver side, it equals the received power density times area of the receiver side, right? So for the receiver side, the actual area of the receiver, we use AR, theta, and phi to represent it, and it is related to lambda square over 4 pi times the gain of the antenna on the receiver side. So I'm not sure whether you remember this equation here. So this equation is the our previous investigations in there for the propagation of electromagnetic waves. So this one, and after that, in the case of the polarimetric radar systems, we really used something to represent the beam pattern. All right. So for the single polarized communication, the radar systems, we already use the radiation pattern, right? Use the radiation pattern, and we use the J theta phi to represent that, right? It can be for a typical radar system, we really use a sync function to represent that, right? So for the polarimetric radar systems, because it has two polarizations, the dual polarization, so we do not use a function, radiation function, pattern function. Or we're going to use the pattern matrix. To represent that. On the pattern matrix, we use capital F to represent it. So the matrix like this one, and it has, because it is dual polarized, so it should have 4 elements, right? Elements for both H polarization, both V polarization, and cross polarization, another cross polarization, right? So this is the copolarized and the cross polarized components. So we have 4 elements, and for each element, it has their expressions for as function, the pattern function, correlated to that one. And so now, for the general expressions for the pattern matrix, we have it being like this one. Yes, the F. We use F, P, and Q. So P and Q represent the range of the one of the polarizations for H and V, right? So P and Q can be equals H or V. H can be expressed as the gain, right? At 0 initial, and the maximum, and also PQ theta phi. And this term is not identical to this term now. it has a new name. It's called a normalized pattern function. So this is the expressions here. And so now we have 4 terms. And for the radar systems, what we want to do actually for our previous radar system, for example, for the single polarized systems, we want it to have a perfect isolation on the polarizations, right? So we wanted to suppress the vertical components and just want the directions that we used or we interested to pass through it. So for the polarimetric radar systems, it has another important fact is that the design of the systems makes it have a very good suppressions on the cross components. So why it has such configuration or it has such function on that is because let's look at the radiation pattern here. So this term is for the copolarized components, the radiation pattern, and this one is for the cross-polarized. So for the cross-polarized components, we can see that. So it has null at the beam axis, all right, for the cross-polarized patterns, and also it has 4 lobes, 4 equal lobes. And these 4 equal lobes, they have the alternate phase that it can cause constellations for the strongest cross-polar components. So this means if we used the polarimetric radar systems, it can offer for this kind of radar the WSR. The WSR radar systems, it can lead to an isolation for the polarizations is around 40 dB. So this is very high, all right? Especially when we wanted to obtain the details about the hydrometeors, we need a very high polarization purity. So this configuration is very useful and mostly employed. So now we get the expressions for the electric field and the power density and also the power and the transmitter side. For the detections for the radar systems, we already obtain the voltage information or the complex voltages. So the complex voltage. So for the complex voltage at the receiver side, it can be expressed as V and P and Q. PQ corresponds to the polarization of H, and it can be expressed as, firstly, as related to the electric field, right? Electric field. And the electric field here is the scattered electric field due to the scattering effects caused by the hydrometeors. So we needed to sum all the scattering components here because we already set it, okay, the total infinity, okay. And also another thing is directivity, dipole, and also the intrinsic of the square root of the intrinsic impedance. Looks like this one. So if we wanted to express it as another configuration as the polarimetrics, all right? So it's related to the polarimetrics also, and this equation can be expressed as 8 pi times eta node, and also the sum of L with respect to 1 over r squared times the matrix, and also another matrix transmitter side. Okay, so the transmitter side and the receiver side, and also the scattering field or the scattered field here. So this one is a complex value S prime. So S prime is also, we really can express it as Ps, the scattered power. So now, if we want to express it in the matrix format, so it can be expressed as the diagonal for the copolar, and this one is the cross polarized components. It equals lambda over 4 pi r squared and times the square root. The transmitted power here, this time equals as soon as m hydrometers, the number of the hydrometers here, and so here is the expressions for the S prime HH, the diagonal, or the copolarized and the cross-polarized here. So this side is the matrix, the polarimetrics here, as we introduced previously. So this is the expressions for that one. So that means if we want to do the analysis on the polarimetric radar systems, we need to know the matrix calculations, all right? Familiar with that one. So now, if we want to express the electric field that was expressed when we obtain the complex voltage values on here, so we wanted to express the received power as polarization P. So it expresses and it obtains related to the voltages, right? Square of it, and we take and obtain the ensemble values on that one. So it is expressed like this one, and I wanted to just get you the final result. This one, the transmitted power times the complex values here. So the gain values, the beam width, the pulse width, and also the 4 pi r square, and the distance square times 16.2 here. And also we have another term is theta p q. So here we release the received power with respect to the transmitted power, right? So another thing that we wanted to introduce is how this factor is. So if we, for the ratio between the transmitted power and the received power, we get this one is called the radar reflectivity. radar reflectivity. So this one, theta 1, is the 3 dB beam width, and tau is the pulse width. Pulse width here. So now this equation is called or serves as the polarimetric weather radar equation. Metric weather radar. Weather radar equation here. So now we get the general equations, a general expression for this equation. We want to introduce how to obtain all the other parameters, right? Our estimates based on our measurements and how it works. But before that, we need to introduce the algorithms of the different operation mode. So this section we want to introduce is the polarization modes for study. So the first one is called the eta. Eta means, A means the alternate, and T is transmission, A is alternate again, and R is reception. Okay, so from the physical meaning of this term, that means we have one transmitter and one receiver only. So for the transmitter side, it can detect the transmit the wave components of vapor, and the receiver side vapor. And also the transmitter can be vapor, the receiver can be H-pole. And also the transmitter can be H-pole, and the receiver can be vapor and H-pole. So that means we get the components H, right? So we get expressions for the voltage, like this one. So for this one, each time there are only one transmission and one receiver, one reception here. So this is for the eta mode, and the second mode is called TSR mode. So for this mode, and we just wanted to introduce this term. It is called simultaneous. So for this condition, we get one transmitter and two receiver. That means we have transmitter at V polarized, which relates to the V and H components. And for H polarized, we have the same thing, V and H polarized. So we can get the H, HH. We have four components like this one, right? So this is the second mode. And the third mode has its own name. Is simultaneous transmission, simultaneous reception. Okay, and for this condition, it has two transmitters and two receivers. And two transmitters with each, two receivers with each polarized component besides it, and each of that related to each other. So we get only with each we have two components. The values is just the cross-polarized components only. So the copolarized components only. So only copolarized components mirrored. And the cross-polarized components is not mirrored, but it exists actually for the radar systems. So this is the most. This is the currently adopted by the most polarimetric radar systems operates, and also it includes the our previous WSD 88, the WSR 88D radar systems. So the main advantage of that one is why we use this configuration instead of the other two is because under such configurations, it do not need, the first one is do not need the power switch. Which is very expensive. This is one of its advantage. Another thing is that it is very easy to implement, very easy for implementation or easy to implement. And compatible with the previous other configurations also. So this is its advantages, and besides that, advantages. It also has a disadvantage. Its disadvantage is only one. That is related to the polarization purity. So the polarization purity, it should be 40 dB. It's very high than the 20 dB for other radar systems. So this is disadvantages. So now, if we get the expressions, we get the operation modes for the polarimetric radar systems, we wanted to do as we can also obtain the measured voltages, the complex voltages, and we can obtain as the following power, related power, and we next as we wanted to do is the data analysis, right? So the first thing that we need to do is the regular estimation on the radar variables. To the radar variables. So if there is an expressions, this expression is it was expressed in the previous conditions that if the complex voltage follows So the complex voltage here is related to the scattered wave like this one. So it follows the same distribution with the scattered waves. Alright? So, and also we really express that in a Gaussian form. Okay. So now if we wanted to do further is we wanted to get the correlation function of with the radar system, right? We want to get the correlation function. We express it as time interval delta t equals 1 square ensemble. Okay. Scattering instant. This is the term, so it's not a value. So minus kd square sigma v square times delta t square over 2 e argen kd times we are as the Doppler velocity times delta t here. So here we are as the Doppler velocity here, and the sigma v is called the spectrum width. Okay. Now from this equation we can see that the correlation functions of the weather radar signals follow the Gaussian function also because it's related to the scattered field here. So now it is extended to include the two kinds of the correlation functions. Previously we learned most commonly used is the autocorrelation. Function named as ACF, and now we use as the cross correlation function named as CCF. Okay, so the CCF we really used a term to represent that. So the first before that is we need to define several parameters. The first one is for radar systems, we used a time lag, right? So the time lag is related to use tau to represent that. It equals the number of the lags times TS. TS is another important thing. That's the pulse repetition. Rate time. So we call it PRT yearly. And KD in this expression, it equals, previously we know that K, right? It represents the wave number and allows the flow of the power in a medium. But here it should equals 2 times K here. So it equals, it previously is 2 pi over lambda, right? Now it becomes 4 pi over lambda. So this is for the backscattering components. Okay, so now let's take a short break. I'm going to Continue after 5 minutes. Okay, now let's continue. So, okay, now let's continue with that. So the time correlation function can be, or the term can be expressed as rho, or the time n times ts, the a time lag, and that can be expressed as e to the power minus 2k square times sigma v, the spectrum width square, okay, and n times ts square also, and finally it can be expressed as minus 2 same square and n ts square can be expressed like this, but here we added a term. It is called this one. It is called the torsi. It's equals lambda over 4 times pi times sigma v. It has its own name. It is called correlation time. Correlation time here. And lambda is definitely the wavelength, and sigma v is the spectrum width. All right. So usually for these systems, we need to know that the phase, it usually wraps around every 2 pi. All right. So this yielding a radial velocity that is limited. The radial velocity, it is limited with e, the next velocity is minus n n, and I have n expressions for the term within h equals lambda over 4 times second time, this one. So now that means the term of e minus alpha e2 times j k v r n t can be expressed as exponential of e to the power n times j n r, like this one. So this is the expressions for this term. So now, if we wanted to extend the expressions here, this. So for the autocorrelation function, the expressions here. So now if we wanted to do the estimates or the estimating on this function, so we can get its expressions for the ACF and further for the CCF. So for the ACF, expressed by R, again, H weight, okay, and related to the number lag, and it can be expressed as the from the autocorrelation. All right, correlation means we have two terms. The first term is at time t related. The second term is time t plus n times ts, right? So the definition of them, and so it's simple, that one, and it can be expressed as expressions, and also the cross correlation. The cross correlation is also h weight, same thing, and ts. But for the cross correlation, we have only the there is H. The cross correlation, we have the same thing, like this one, A plus N minus V D. All right, but we only consider the cross. So this is H, this is V, and the ensemble of it. This one. So now, based on our previous expressions for the voltages, it expressed as SHV times the TS, right? The time correlation times the exponential of J pi VR divided by Vn, the Nyquist velocity, and this one is cross, so it's FH times SV, both of that one, real HV again, and also the exponential. The term H is has J pi N VR divided by Vn. But there is another difference between both. You know why? The advantages for the cross polarization with respect to the autocorrelation is due to the autocorrelation has another term that we do not want. It's the noise. It has noise in the term. And for the cross polarization, the cross correlation term, it has another term. Is because of cross, so it has a differential phase, like this one. Differential phase, phi dp. Okay, now this is the general expressions or the equation, the formulas for both parameters. So now if we want to take it to that one and estimate it based on the measurements, so what we need to do is we wanted to take it out from the in-sample average, right? So here is the in-sample average. We want to take it out from the in-sample average and take the take it to be summary of many other components with respect to each of the samples or each of the legs. So we get expressions. Estimated value. Estimated. So we have a DAG to represent that, and DAG to represent it. Okay, and H we have N samples. We have H we N samples again. So it is expressed as the correlation between V star T plus T plus N times TF. We use N to represent that one, and we use capital M to represent the total number of pulses. And here the same thing, H we and we use N to represent the time shift for that one, N times TS. Okay, and here is the same thing. H star this term is VH. Sorry, this should be not this one. And so we have taken a summary of that, and of course from 1 to minus n, same thing, and from 1 to n minus n. So average value like that one. Okay. And term to represent that one is total number of processes, and m is the time shift related to the due to the multiple of the process, right? So this is the expressions for the estimates of the autocorrelation function and the cross correlation function here. So once the correlation estimates are obtained, the polarimetric radar system, the variables of the polarimetric radar systems can be estimated, and the moment is also the same thing. Here we come to here to see this one, because for the autocorrelation part there is a noise term here, and for our following estimates we set it to be 0. So just want to simplify it just on that one. So now the first thing that we want to concentrate on is the we're going to follow all these things, the reflectivity, and also velocity, and the correlation coefficient, we get that one, and also the differential phase, all these terms. We're going to get the expressions for that. Okay, now the first thing is we wanted to get is the power, the total copolarized power. Okay, the total copolarized power, we use H way to represent that. So the total copolarized power is can be obtained from the average of the instantaneous powers, the average of each. So that means instantaneous, this one, and it can be expressed as 1 capital M sigma plus 1 to capital M, and the square of each. So now if we want to take an average for the average, the further average of each. The further average on each. We take average on each. So it can be expressed as one to M average of this one. All right. So the average, if the average is taken into a unit area, it can be expressed as the power density. This one. So this is the expected values for it. So now we wanted to do as we wanted to get the variation of the power. So use the AR represented like this one. If we have the variation components, I think most of you knows how to calculate that, right? Shows the average of this one minus average of this one, right? So based on these terms, I get it to be square divided by mi. So the mi, it has definition as its own definition as mi, and expressed as T d divided by pi times tau c. Okay, and the Td, it has its own name as the direct time, and the tau c, as we mentioned previously, it is called the correlation time. So we have the variance we usually do as the standard deviation, right? We use SD to represent that. And it can be expressed as the same thing. Standard deviation is the square root of this one. So it can be expressed as h, the square root of this term. So here as square root of mi, this one. Okay, now we have all these terms. We can further do is we wanted to introduce how these terms, the variables affect the measurements. So for a higher spectral width, as we come back to so the spectrum width, it is usually relates to the velocities of the particles. So the higher spectral width, for example, the particles have can be applied for the particles that have a higher velocities. So this is gonna related to a very short correlation time. On the opposite side, if the process, if the spectrum velocity, the spectrum width is small, for example, if it is small, that means we only use it for the Doppler mode, so that the power signals are highly correlated, and it is more convenient for us to obtain the accurate velocity estimations, the radial velocity estimations. And on the larger spectrum width, that means it's gonna be used, or it can be helpful to avoid or to reduce the range ambiguity and maintain the independence of each components of each particles. So this is used for the surveillance. Right, so the spectrum width determines how the radar systems, or the main goal or the main target of the radar systems that can be used. Now we need to come back to our analysis, right? Because here we wanted to analyze. What we wanted to analyze is the reflectivity instead of the power. All right. So we have the reflectivity. We use zeta, capital zeta, to represent that, right? So estimated HV. So we have the standard deviation of H. It can be expressed as 10 times log 1 plus 1 over square root mi. Reflectivity here. So this is the reflectivity. And also, another thing is, this is standard reflectivity. Another term is the differential reflectivity. So for the differential reflectivity, H times 10 times log the variation of differential is the difference between H and the differential between V. All right. So we further take the ensemble average on H. Ensemble average on H. So it can be ensemble H, ensemble of V, like this one, and it equals the average by the detector, right? The time averaged by the detector, and so then the time averaged by the radar systems, like this one. And now, if we wanted to do is, we wanted to analyze how, for example, the flowing or the distribution or the intensity of the weather conditions should always be random. So there are some fluctuation, all right, fluctuating error for this term. So the error we really express it as R to represent that. Okay, so it fluctuates due to the both components, right? So that means partial theta dr, partial pH, delta pH, plus partial theta dr, or partial PV, delta PV, like this one. And finally, it becomes like this one. Minus PV, expressions for this term. So this is the differential reflectivity, and according to the previous expressions, we have the variance of the differential reflectivity and the standard deviation of differential reflectivity. So it can be expressed as 10 ln 10 square times over I times 1 minus rho HV squared. So the rho HV is the correlation time, the time correlation, right? And this term is just the square root of this part. So it is 4.343 times square root 2 over mi 1 minus rho hv squared, like this one. So that means 10 over ln 10 is 4.343. Remember how this is related? Would you? How's the 4.343? How it is related? Could you remember? The translation between the nipple to decibel, right? So 4.343 times 10 to the power 3, the unit transform. So now we have an expression for the this term rho hv. So could you remember what rho hv is? We mentioned previously. So the copolarized correlation coefficient, right? So it has its own expressions for the estimates. We can estimate it at rho hv. It's related to the cross instantaneous and the average, the absolute of h divided by the estimations for the power h and power v or so, and then the standard deviation of h is related to the square root, actually 1 minus root square over 2 times mi. So this is for the, and another thing is the differential phase, all right? So for the differential phase, the estimation of h we use 5 differential phase that to represent that. It is related to 180 to pi times the phase part of the cross chloride, the instantaneous cross pole of h. So why we are also interested to the differential phase is because it can help us to obtain the or to quantify the precipitation rate, of hydrometeors. Okay, and its standard deviation can be expressed as 180 divided by pi coefficient 1 minus hv squared divided by 2 times mi. Okay, now we get the expressions for the differential phase. The last one that we want to know is the Doppler velocity. So the Doppler velocity is r, yeah, and also the spectral width so it's related to the hv and that's related to the ts, the phase times lambda over the 4 pi ts. This term is related to a little bit complicated, but we can express it as 2 times ln r hv 0 divided by r hv ts times lambda over 4 pi ts. Okay, so this is the expressions for the radial velocity or the droplet velocity along the radial direction. Okay, so this is the expressions for the basic parameters of variables that should be estimated based on the measured complex voltage by the radar systems. And so we also need some more algorithms to obtain how this affects or how it affects by the other systems that like the noise. As we mentioned previously, that we set the noise to be 0 for the simplification of our analysis or our demonstrations. But actually, for the radar system, the noise, it can cause some bias and also can cause some extra errors that in the moment or the variable estimates. And so what we need to do is we need to correct this bias caused by the noise. And so, for example, if we can subtract the noise from the received power, right? So if we wanted to do that, we need to know we need to perfectly characterize the noise. And so if, as we mentioned previously, the noise is represented by this one, right? So we need to subtract it by initial minus h, okay? And we get the final power, the corrected power, as we use a superscript C to represent the corrected power. And so based on this one, we can get new expressions for the reflectivity, the differential reflectivity, the corrected term, and also the correlation coefficient, the corrected term. Okay, and it can be expressed as the initial differential part, right? The initial differential part, and the initial correlation coefficient subtract the noise, the influence by the noise. Here, we take like 10 times log 1 plus 1 minus S and R at the V pole, S and R at the H pole. This one is the same thing. Square root of 1 plus 1 over S and R V pole. 1 plus 1 over S and R for H pole. So this is the correlations for this part. And another thing that we wanted to introduce is the correlation, the terms that we used multiple correlation estimates. The multiple correlation estimates. For that one to further improve it. Okay, so this is the analysis for the measurements of the radar systems. And now the last thing that I want to introduce is about the final